Some of the most powerful players in chemistry are also, well, the most familiar. Think about salt. It's essential for life, right? A staple in every kitchen. But have you ever paused to consider the incredible elements that actually make it? Today, we're diving deep into Group 17 of the periodic table, a remarkable family known as the halogens. The name itself, halogen, it's Greek, meaning salt givers.
Exactly. And for this deep dive, we're digging into a real cornerstone text, Shriver and Atkins Inorganic Chemistry. Our goal here is to break down the systematic features of these elements, fluorine, chlorine, bromine, iodine, and even astatine in a way that's clear, engaging for college students, helping you really grasp their unique properties, their compounds with oxygen, and that fascinating world where halogens combine with each other, the interhalogens. By the end, you should have a solid understanding of why these elements are just so vital, from industry right down to the air we breathe.
Okay, let's unpack this. Get ready, because we're going to uncover some surprising facts and connect the dots on these incredibly reactive nonmetals. So, Group 17, what's the first thing we should really get our heads around?
Right off the bat, these are all nonmetals, and they are super reactive, seriously reactive. Just think about them at room temperature. Fluorine and chlorine, poisonous gases. Bromine is this toxic, volatile liquid. And iodine is a solid, but it readily sublimes, turns straight into this, intense violet vapor. Astatine, well, it's the heaviest, highly radioactive, not studied as much, so we'll mostly focus on the others. And the key thing is they're really keen to react because they're just one electron short of a full outer shell.
Ah, that makes sense. So they're electron grabbers.
Totally. Which means their compounds, especially the ones with oxygen, the oxoanions we'll talk about, are often powerful oxidizing agents. They just love accepting electrons from other things.
Okay. And when we think about how these elements bond, how they form molecules, is there a tool to help us picture that?
Yes, absolutely. The VSBR model, that's valence shell electron pair repulsion, is incredibly useful here. It helps us predict the actual 3D shapes of the molecules they form, whether it's halogens with each other, with oxygen, or even with noble gases like xenon. It's based on a really simple idea. Electron pairs around the central atom repel each other. They push each other as far apart as possible, dictating the molecule's geometry.
And knowing the shape helps us understand how it reacts.
Exactly. Shape is crucial for reactivity.
Okay, let's zoom in on the elements themselves. What are the sort of fundamental atomic characteristics that define this group, their chemical DNA, if you like?
Well, they all share that distinct outer electron configuration, ns²np⁵. This gives them some shared properties. Really high ionization energies, it takes a ton of energy to pull an electron off. Very high electronegativities, they strongly attract electrons when they're in a chemical bond. And generally high electron affinities, meaning they're pretty eager to gain that one extra electron to fill their outer shell.
Right, they want that stable configuration. But here's where it gets interesting. Fluorine, the little one at the top, it seems to be a bit of an outlier, doesn't it? Almost a rebel in the family.
Ah, you've nailed a really key point there. Fluorine absolutely shows several anomalies. It behaves differently. Surprisingly, its electron affinity is actually lower than chlorine's.
Wait, lower? But it's the most electron negative. Shouldn't it want electrons the
You
most?
could think so, wouldn't you? But fluorine is so small, its outer electron shell is really crowded. So when you try to stuff another electron in there, you get significant electron repulsion. It pushes back. In the larger chlorine atom, there's just a bit more room, so that repulsion is less of an issue. This crowding effect also contributes to the F-F bond in F2 gas being unusually weak, much weaker than you'd expect.
That's really counterintuitive. So, okay, weaker bond, less keen on grabbing an electron than chlorine. Does fluorine still pack a chemical punch?
Oh, absolutely. Don't underestimate fluorine. Despite those points, metal fluorides often have greater energies of formation. They release more energy when formed than the equivalent metal chlorides.
How does it work then?
It comes down to the overall energy balance. Fluorine's lower electron affinity is more than canceled out by two huge factors. First, the lattice energies of ionic compounds formed with the tiny fluoride ion, F, are incredibly high. That small size leads to very strong attractions in the crystal. And second, the covalent bonds fluorine forms, especially with metals in high oxidation states, are exceptionally strong. So when you add it all up using thermochemical cycles, forming something like sodium fluoride releases more energy overall than forming sodium chloride, largely thanks to that tiny, powerful fluoride ion.
Fascinating. So it's this complex interplay of factors.
Precisely.
Okay, so these things are super reactive. Where do we actually find them in nature? And, maybe more importantly, how do we get them into a form we can actually use?
Good question. Because they are so reactive, you'll basically never find them just hanging around as free elements. No F2 gas floating about. They're always locked up in compounds, primarily as halide ions. So chlorine, Cl, bromine, Br, and iodine, I, are abundant as anions, those negatively charged ions in the oceans and in salty brines. Fluorine is mainly found in minerals like calcium fluoride, which is fluorite. Iodine can also pop up as iodate in some nitrate deposits.
And getting them out. Industry must have ways.
Oh yeah, commercial production is massive, especially for chlorine. For fluorine and chlorine, the main method is electrolysis, zapping their salts with electricity. For fluorine, though, you can't do it in water because water would react first at the electrode. So they use a molten mixture of potassium fluoride and hydrogen fluoride, very carefully keeping the resulting fluorine gas separate from the hydrogen gas they react explosively.
Yikes. Okay, what about chlorine?
Chlorine is mostly made by electrolyzing salty water, aqueous sodium chloride solution. That happens in what's called a chloralkali cell. It's a neat process that produces chlorine gas, hydrogen gas, and also sodium hydroxide, which is really useful industrially. They use special membranes to keep the products apart.
And bromine and iodine, not electrolysis.
Generally not. They're typically recovered by chemical oxidation. You use a stronger oxidizing halogen, usually chlorine, to kick the bromide or iodide ions out of solution in seawater or brine. So chlorine gas bubbles through, steals the electrons, and forms Br2 or I2, which can then be driven off maybe with a stream of air.
Clever. Using a halogen to make another halogen.
Yep, displacement reaction.
Okay, so we've got the elements. Let's talk about the simple compounds they form. What are some key examples, and what do they tell us?
Right, let's think about oxidation states first. Fluorine, remember, is the king of electronegativity. It always has a NaCl oxidation state in its compounds, always. But the others, chlorine, bromine, iodine, they're much more flexible. They can range from -1 all the way up to a surprising +7.
+7, wow.
Yeah, that versatility is key to their rich chemistry. And fluorine's properties, high electronegativity, small size, have a huge impact on the compounds it forms. It tends to make acids stronger. If you put fluorine atoms on an acid molecule, like in trifluoromethensulfonic acid, it becomes a much stronger proton donor, a stronger Brensted acid. It also boosts Lewis acidity, the ability to accept electron pairs. Antimony pentafluoride, SBF5, is an incredibly strong Lewis acid because of the fluorines, and it's brilliant at stabilizing elements in unusually high oxidation states. Think uranium hexafluoride, UF₆, vital for nuclear fuel.
Okay, what about something really common like the hydrogen halides? Hydrochloric acid, for example. Do they all act the same?
Not at all. Big differences here. All the group 17 elements form these hydrogen halides, HF, HCl, HBr, HI, but hydrogen fluoride, HF, is really the odd one out, primarily because it can form extensive hydrogen bonds between molecules. This makes it a liquid at room temperature, while HCl, HBr, and HI are all gases.
Hydrogen bonding, that powerful intermolecular force.
Exactly. It gives HF a surprisingly high boiling point and a wide liquid range, making it a useful non-aqueous solvent sometimes. But here's another twist. In water, HF is actually a weak acid.
Weak? I thought hydrofluoric acid was notoriously nasty stuff.
It absolutely is. Despite being a weak acid, meaning it doesn't fully dissociate to release all its H+ ions in water, hydrofluoric acid is one of the most toxic and corrosive substances known. It attacks glass readily, which is why it's stored in plastic containers. And it's dangerous because it can penetrate skin easily and cause deep tissue damage, even pulling calcium out of bones. Horrible stuff.
Okay, noted. Avoid HF. What happens when halogens meet oxygen?
Well, they do form binary compounds with oxygen, but most of them are pretty unstable. Chlorine, for example, forms a whole range of oxides with different oxidation states like ClO2. But almost all chlorine oxides are endergonic. They actually require energy input to form, meaning they're thermodynamically unstable, and they're often explosive when heated. Handle with care.
So not very stable.
Generally not. Iodine oxides are the most stable of the bunch, with I2O5 being an important one. It's actually used in analysis. And then you have the oxoanions and oxoacids. These are really important. They feature oxygen atoms bonded to the central halogen atom. Think of ions like hypochlorite, ClO, chlorate, ClO3, or perchlorate, ClO4, or the corresponding acids like hypochlorous acid, HClO, or perchloric acid, HClO4. Perchloric acid, HClO4, is a very, very strong acid. And a key takeaway, all these oxoanions are powerful oxidizing agents.
Oxidizing agents again, that seems to be a running theme.
It absolutely is for the halogens.
Okay, this next group sounds intriguing. Interhalogens. It sounds like a chemical family reunion, maybe a slightly dysfunctional one. Halogens bonding with other halogens.
Yeah, you could put it that way. They are fascinating. These are molecular compounds formed between different group 17 elements. They typically have formulas like XY, XY3, XY5, and even XY7. Usually the heavier, less electronegative halogen plays the role of the central atom, X, surrounded by the lighter, more electronegative ones, Y. These compounds are often highly reactive intermediates in chemical reactions.
So how do these different types behave, like XY versus XY5?
Well, the simple diatomic ones, XY, like chlorine monofluoride, ClF, or iodine monochloride, ICl, can be formed from most combinations. Their properties are often sort of intermediate between the parent halogens. ICl, for instance, is deep red, kind of halfway between yellow, green chlorine, and dark purple iodine. When you get to the higher inner halogens, XY3, XY5, XY7, most of them are fluorides. The central atom is surrounded by fluorine atoms. The only known neutral example with the central atom in the maximum +7 oxidation state is iodine-heptafluoride, IF₆.
Only iodine. Why not chlorine or bromine heptafluoride?
Good question. For chlorine, putting 7 fluorines around a relatively small period 3 atom leads to too much crowding and electron repulsion. It's just not stable. For bromine, well, bromine is a bit reluctant to reach its absolute maximum oxidation state. That's another example of what chemists sometimes call the alternation effect. Elements in the middle of a block, like bromine here, can sometimes find their highest oxidation states less stable than expected compared to elements above and below them.
Interesting. And what about their shapes? Does VSEP still work?
It works remarkably well. For example, XY3 compounds like ClF3 have 5 electron pairs around the central chlorine, 3 bonding pairs, 2 lone pairs. VSEP pair predicts a trigonal bipyramidal arrangement of electron pairs, leading to a molecular shape that's described as a bent T. XY5 compounds like BRF5 have 6 electron pairs, 5 bonding, 1 lone pair, giving a square pyramidal shape. And IF₆, with 7 bonding pairs, is predicted to be pentagonal bipyramidal. These specific, often unusual shapes are absolutely critical to understanding how these reactive molecules behave.
And are there ions involved too, like charged interhalogens?
Yeah. Yes, indeed. Beyond these neutral molecules, you can also get polyhalide ions. These can be calcifications, positively charged, like I3+ or I5+ air, which have bent structures, or more commonly, anions, negatively charged, especially for iodine. The most famous is the triiodide ion, I3. You make it by dissolving iodine, I2, in a solution containing iodide ions. VSEP predicts I3 to be linear, with the central iodine having 3 lone pairs in equatorial positions and the other 2 iodines bonded axially. But what's neat is that the exact bond lengths and angles in these polyhalides can actually change depending on what positive ion, the counterion, they're paired with in the crystal. It shows the bonds are relatively weak and flexible.
So quite complex behavior.
Definitely. A lot of subtle structural chemistry there.
Let's switch gears slightly. Fluorine, you mentioned its anomalies. What else makes fluorine and its compounds so special, this fluorine effect?
Right, fluorine compounds often do have these special properties. One big one is their high volatility. Many molecular compounds containing fluorine just evaporate very easily, often more volatile than the equivalent hydrogen compounds, and much more so than the chlorine ones.
Why is that?
It's because fluorine atoms are small and hold on to their electrons very tightly. This means they have low polarizability. The electron cloud isn't easily distorted. Low polarizability leads to weak intermolecular forces, specifically weak London dispersion forces between the molecules. So they don't stick together well and easily escape into the gas phase. Unless hydrogen bonding is involved. Hydrogen fluoride, HFs, is the big exception. As we said, it's a liquid due to extensive hydrogen bonding, giving it that wide liquid range and making it a useful solvent.
Okay, so volatility is one thing. What else does fluorine do?
Well, its powerful electron withdrawing ability really kicks up the acidity of compounds. Put fluorine atoms on a molecule, and if it's a Brunstad acid, it becomes a much stronger proton donor. Like trifluoromethane sulfonic acid is way stronger than regular methane sulfonic acid. Same effect for Lewis acids. Fluorine enhances their ability to accept electron pairs. And we mentioned its knack for stabilizing high oxidation states, IF₆, UF₆, PTF6, compounds that often don't exist with other halogens.
And it dislikes low oxidation states.
Generally, yes. It tends to disfavor them. We saw the copper I-fluoride example. It's unstable and disproportionate, reacts with itself to form copper metal and copper perfluoride. Copper-1, chloride, bromide, and iodide, however, are perfectly stable. This comes back to lattice energy. The tiny F ion, paired with a small, highly charged cascation like Cu2+, gives a huge lattice energy, making the higher oxidation state, Cu2+, thermodynamically much more favorable than the lower one, Ke+.
It all ties back to that small size and high electronegativity.
Pretty much. Those are the keys to understanding fluorine.
And of course, we have to talk about fluorocarbons. These have made a massive impact from kitchens to, well, the atmosphere.
Absolutely. Fluorocarbons are organic compounds where some or all hydrogens are replaced by fluorine. Their defining feature is the incredible strength of the carbon-fluorine bond. This makes them very resistant to oxidation and chemically inert. Historically, this stability was exploited to make chlorofluorocarbons, CFCs, and hydrofluorofluorocarbons, HCFCs. Think freon refrigerants, aerosol propellants. They were everywhere.
But they had a dark side.
A very dark side. It turned out that CFCs, being so stable, could drift all the way up to the stratosphere unchanged. Up there, intense UV radiation breaks them down, releasing chlorine atoms. And these chlorine atoms act as catalysts, destroying the protective ozone layer very efficiently. One chlorine atom could destroy thousands of ozone molecules.
Leading to the ozone hole and international action.
It's exactly. The Montreal Protocol led to a global phase-out of CFCs and HCFCs. They're now being replaced largely by hydrofluorocarbons, HFCs, which don't contain chlorine and thus don't deplete ozone. Though HFCs themselves are potent greenhouse gases, so that's another issue.
Right. And the other famous fluorocarbon application.
Teflon. Polytetrafluoroethene, or PTFE. It's this remarkable polymer, chemically almost wholly inert, stable over a huge temperature range, great electrical insulator, and famous for its incredibly low friction, its non-stick quality.
Why is it so slippery?
It's thought that the fluorine atoms, which are just the right size, form a really smooth, tightly packed sheath around the carbon polymer backbone. This dense fluorine sheath minimizes the intermolecular forces between the PTFE surface and anything touching it, so things just don't stick. It's used in so much more than cookware, Gore-Tex fabric, seals, bearings, electrical insulation. A truly unique material.
Amazing stuff derived from that unique fluorine chemistry. Okay, let's quickly revisit the oxoanions. You mentioned perchlorate being a treacherous ally. Why so dangerous?
Yeah, that's crucial. Perchlorate ions, ClO4, are thermodynamically powerful oxidizing agents. While solutions might seem fine, solid compounds containing perchlorate, especially mixed with anything that can be oxidized, like organic material or certain metal ions, are incredibly hazardous. They could be metastable, they sit there looking stable, maybe for years. But then a little bit of energy input, a shock, friction, heat, even static electricity can initiate a reaction. And once it starts, it can detonate with devastating force. Many accidents have happened. Chemists need extreme caution. Safer alternatives like triflate are often preferred now if possible.
Definitely something to respect. And perbromate is even worse.
Even more oxidizing, yes. BRIO4. Its synthesis was a challenge only achieved in the late 60s. Its instability compared to perchlorate, BClO4 and periodate, IO4, is again likely linked to that alternation effect for bromine. Periodate IO4, on the other hand, while still a strong oxidant, reacts much more rapidly and controllably than perchlorate, making it useful in analysis.
So the reaction speed matters as much as the potential power.
Absolutely. Thermodynamics tells you if a reaction can happen, kinetics tells you how fast. For these oxoanions, there are general trends in rates. Usually, oxidation reactions get faster as the halogen's oxidation number decreases. So hypochlorite, like in bleach, reacts much faster than perchlorate. Also, the heavier halogen oxoanions tend to react faster, especially in high oxidation states. That's why periodate is faster than perchlorate. The iodine atom is just bigger and more accessible for reaction compared to the chlorine atom buried inside the perchlorate's oxygen cage.
Okay, and finally, let's touch on structure again. You mentioned layered structures for some metal halides.
Right. It shows how bonding changes across the group and with oxidation state. Metal bifluorides often have these highly symmetric 3D ionic lattices, like fluorite or rutile structures. The bonding is pretty close to purely ionic. But as you go to dichlorides, dibromides, diodides, especially with D-block metals, you often get layered structures, like the cadmium iodide type. This indicates more covalent character and different bonding interactions. Same pattern for trihalides. Trifluorides are often 3D ionic networks, while the other trihalides tend towards layered structures. And as the metal's oxidation state gets really high, like +5 to +6, the halides become molecular covalent compounds, like WF6 or MoFs, which are gases or volatile liquid solids. It shows a clear progression from ionic towards covalent bonding as you go down the group F to I and as the metal's oxidation state increases.
A nice summary of the trends.
Yeah, structure and bonding are always linked.
What a journey through Group 17. Seriously, we've seen how these salt givers, from, the weirdness of fluorine to the explosive tendencies of some chlorine compounds, they shape so much of our world. We've covered their atomic quirks, the complex dance of the inner halogens, and their huge impact, everything from toothpaste to the ozone layer. It really shows how even elements we think are familiar hold this whole universe of complex, fascinating chemistry.
Absolutely. And understanding these halogens, their reactivity, why they form the structures they do based on models like VSEPR, their uses, their dangers, it really highlights how interconnected inorganic chemistry is. And I think it also underlines why we need to think critically about chemical advancements and their impact on the environment, like with the CFC story.
Definitely. So what does this all mean for you listening? Well, maybe the next time you brush your teeth with fluoride toothpaste or use that nonstick pan or even just hear about the ozone layer, you'll have a bit more appreciation for the silent, powerful chemistry of the halogens at work. And it makes you wonder, what other salt givers or reactive families are out there on the periodic table, maybe in less obvious corners, just waiting for us to uncover their own hidden depths and unique stories? From all of us here at the Deep Dive and the Last Minute Lecture team, thanks so much for joining us.